I almost never get the question, what's not going to change in the next 10 years? That second question is actually the more important of the two.
Jeff Bezos was talking about retail, but 15 years ago I got advice that taught me this lesson the hard way in software development. An old school manager handed me a 5-page guide and said something that made zero sense at the time. If there are no issues in your project, you are a bad manager. We thought he was crazy. Today's wisdom says the opposite. No issues mean you're killing it, right? Today, I will share 5 old-school engineering management principles that I still use and believe will remain valid no matter what technology changes comes next. Truth number 1. If you can't trace it, you can't control it. August 1st, 2012. Knight Capital, 440 million lost. A trading firm nearly collapsed because they deployed code without understanding what it would do. The issue? The flag called s'mores that was supposed to be set but wasn't. This flag determined whether the system would use new trading logic or fall back to old dormant code called PowerPeg, a system that had been deactivated years earlier. Without this flag, Knight servers start executing PowerPeg logic. Buy at the ask price, sell at the bid price. The opposite of profitable trading. In 45 minutes, Knights bought high and sold low almost 400 million shares across 154 stocks. The engineers had perfect deployment procedures. They had tested the new code extensively, but they couldn't trace how their new system connected to legacy components. They lost control of what their code actually did. Here's what's terrifying. This wasn't a complex AI system or bleeding-edge technology. This was basic conditional logic, a simple if-then statement that connected new code to old assumptions. AI will write more code. Developments will get faster. Microservices will get more complex. But if you can't trace your logic from requirements through implementation to deployment, you're one misconfigured flag away from disaster. The companies that survive that are ones that can answer, if this changes, what else breaks? Truth number 2. When requirements drift, people get hurt. February 1987, Terak 25. At least 6 people received massive radiation overdoses from a medical device. 3 died. Software had worked fine for years in other machines. What changed? The Terak 25 was supposed to be an improvement. Previous models had software interlocks, physical switches that prevented overdoses, even software failed. But hardware was expensive and bulky. The engineers decided to rely purely on software safety checks. They reused the code from early machines but never updated the safety requirements. The original software assumed hardware interlocks would catch dangerous conditions. When those interlocks disappeared, the assumptions became fatal. The software did exactly what it was programmed to. It just wasn't programmed to the new reality. The Boeing 737 MAX. 346 people died in 2 crashes. The root cause? MCIS system designed to push the nose down if plane pitched too steeply. But the original requirements assumed pilots would always know what MCIS was doing. When Boeing added MCIS, they didn't update the pilot training requirements. They didn't trace how the system would interact with existing procedures. The requirements hadn't caught up to reality. Requirements always drift. Market conditions change. Customer need to evolve. Technical constraints shift. The question isn't whether requirements will change. It's whether you are on track with the change or it will kill your project. Requirements drift happened in the space between what stakeholders think they want and what user actually needs. That the human problem requires human oversight. This can be assisted with technology, but there's a human problem and requires also a human oversight. Truth number 3. Integration failures kill more projects than internal bugs. September 1999. Mars Climate Orbiter. 125 million spacecraft. 4 years of development. 10 months of space travel. destroyed in seconds because Lockheed Martin calculated thrust in pounds seconds while NASA expected Newton seconds. Math was perfect, the physics was correct, the engineering was sound, but two teams made different assumptions about units of measurements and never documented the interface. June 4, 1996. Ariane 5, Europeans' most expensive firework. 50 million rocket exploded 37 seconds after launch. The inertial reference system tried to convert 64-bit floating number to 16-bit signed integer. The number was too large, the conversion failed, the system shut down. The software was perfect, but for Ariane 4. But Ariane 5 flew faster, generating larger acceleration values. The engineers reused tested proven code without tracing the assumption about input ranges. London Stock Exchange 2011. Trading halted for a few hours because software update couldn't handle the message format from another system. Each component worked perfectly in isolation, but when they talked to each other, the message became gibberish. Here's the pattern. Perfect components, fatal integration. Your unit tests pass, your code coverage is 100%, your functions do exactly what they are supposed to do, but System A talks to System B, assumptions collide. Modern systems are more distributed than ever. Microservices, APIs, cloud functions, third-party integrations. Each piece can be perfect, but the connections between them multiply the failure modes exponentially. The companies that scale successfully are obsessed with interface definition, contract testing, and integration monitoring. They know the most dangerous bugs live in the spaces between the components. Truth number 4. Visible problems beat hidden perfection. October 2013. Healthcare.gov. The website that was supposed to transform American healthcare system but couldn't handle day one traffic. Not because of the server capacity, they had planned for high load, but because 55 different contractors built components that couldn't talk to each other. The identity verification system expected one format of data. The insurance marketplace expected another. The payment system expected a third. Each piece worked perfectly in isolation, but the integration was never tested end-to-end until launch day. Every contractor reported no issues in their weekly status meeting. The project dashboard showed green across the board, but the system couldn't enroll a single user. 2013, 40 million credit card numbers stolen. The breach started in stolen credentials from HVAC contractors. The attackers used those credentials to access Target's network, then move laterally through systems until they reached the payment processing servers. Target's security team saw unusual network activity but didn't connect it with HVAC access. Each alert looked normal in isolation. The pattern only became clear after the damage was done. Even though it wasn't a coding issue, it was about understanding the system and monitoring their behavior and connecting the dots of different signals across the board. The old manager understood something profound. It's better to know you have 10 issues than to pretend you have 0. Because those 10 issues exist whether you acknowledge them or not. Most projects are messy, requirements change, dependencies break. People leave, third-party services go down, APIs change without warning. That's not the failure, that's the software development. The themes that survive are ones that surface problem early, when they are still manageable. They assume something is always broken and build systems to find it quickly. Truth number 5. Context matters more than code. Every catastrophic failure I mentioned had perfect code or perfect team or perfect system that did exactly what it's programmed to do. The problem wasn't implementation, it was the understanding. Knight's capital code executed flawlessly. It just executed the wrong logic because of deployment context change. Theorak 25 software worked perfectly. It just worked under safety assumptions that were no longer valid. Mars climate orbiters calculations were mathematically correct. They just used wrong units because two teams had different contexts. Equifax 2017. 143 million Americans had their personal data stolen. Breach happened through a web application vulnerability in Apache scripts. But here's the thing. The vulnerability was known. A patch was available. Equifax had processes to apply security updates. So why didn't they patch it? Because the team responsible for updating Apache struts didn't know this particular server was running a public-facing application. They thought that it was only internal system that could wait for the next maintenance window. They had perfect patch management process, perfect security procedures, but fatal context gap. AI will generate cleaner code, catch more syntax error, maybe even write better algorithms, but it won't understand why you are building what you are building. It won't know your specific strategy of patching servers without knowing the context. Context is everything, and context lives in the connection between requirement, architecture, deployment, and operations. That manager retired years ago, but his advice stuck through every role, every company, every technology shift. For years, I obsessed over finding issues. I became the person who always had a list of problems. My weekly reports looked like disaster inventories, and it worked. We caught problems early, fixed them fast, avoided major failures. But then something interesting happened. 3 years into my current role, I sent my usual weekly report to my boss. For the first time ever, I wrote, "No critical issues this week." My boss called me immediately. "Are you sure that doesn't look like your usual report?" I started to explain, then stopped. The old manager's voice echoed in my head. If you have no issues, you're not controlling your project. But I realized something different. We had no issues because we've systematically solved the underlying causes. Our deployment pipeline caught integration problems before they reached production. Our monitoring surfaced performance issues before user notice. Our requirements process prevented scope creep before it derailed the sprint. That's when I understood the deeper lesson. If you genuinely have no issues in your current scope, it's not time to celebrate. It's time to expand your scope. The absence of the problem isn't the end goal. It's a sign that you're ready for your next challenge. When your current systems run smoothly, that's when you should start asking, what's the next level of complexity we can handle? Maybe it's taking a larger project. Maybe it's expanding to new markets. Maybe it's tackling technical depth we've been avoiding. Maybe it's building the platform that other teams can use. The danger isn't having issues. The danger is staying comfortable when they outgrown the current challenges. What that means for you? The technologies will change, the frameworks will evolve, the methodologies will come and go. But these fundamentals remain. Always document your decisions. Future you needs to understand your current thinking. Plan for requirements drift. They will change. Build systems that can handle it gracefully. Code for the next developer. That person might be you in 6 months. Trace your dependencies. Know what breaks when something changes. Surface problems early. Visible issues beat hidden disasters. Expand when you're comfortable. No issues means you're ready for a bigger challenge. Stop chasing the illusion of perfect projects. Start building the systems that surface problems early and scale with complexity. Build your career around the things that won't change. Everything else is just an implementation details. The companies that survive the next technology shift will be the ones that understand these fundamentals. They will use AI to write code faster, but they will still need humans to understand why they're writing it. They will deploy cloud automatically, but they will still need to trace their dependencies. They will scale to millions of users, but they will still need to surface problems before they become disasters. Master the unchanging fundamentals. Let the tools evolve around them. If you enjoyed this video, I'm sure that you would like to check how good is your software engineering processes. In the description, I left free assessment that will help you understand how your SDLC processes works. Go check it out and let me know what is your score. See you in the next video. Bye.